So good morning. I am Krishna Kumar from Krishna's classroom. So we continue from where we left last time. You recall that we were exploring an example to get some insight into the basis for LBW. So we defined linear transformations from a vector space V into a vector space W. V was assumed to be of dimension n and W was assumed to be of dimension m. And then we called this, we found that the collection of all linear transformations from V to W form a vector space with usual addition and scalar multiplication. Now, the problem then is the one that we usually encounter, namely, what can you say about that dimension of this linear space? This we shall explore, and for that we took a very typical vector space or linear transformations on vector space expressed in the form of matrices. So we made an observation, of course we know this already, that we took dimension m is equal to 2. I'm just simply recalling what we did. N equal to 3 because some problem is involved in fixing the notation. Very handy notation we have to fix. And then we take the field f to be equal to the set of real numbers. Now we see R, we take A from R 3 cross 1 into R 3 cross 1 is the set of all column vectors with 3 rows. And R 2 cross 1 is the set of all column vectors with 2 rows, and in both the cases the entries are from real numbers. Okay. So these are typically, this is of the form that is x1, x2, x3 belongs to y1, y2, now you see that if A is an m by n matrix, or here it is 2 rows and 3 columns, then it defines a linear transformation from R into It is the usual matrix multiplication. A is of the form A11, A12, A13, A21, A22, A2. That is actually 2 rows and 3 columns. Now you can quickly check that it does this, and it's a linear transformation. Then what we did was we looked at a possible, so all elements of L, suppose you take V equal to and W equal to. It's very handy to work it. Then A belongs to L, LVW. This is a typical element of that. We have seen that this is a linear space over R, and we are in fact trying to find out what the dimension of this space is. Now you can see that A can be written as a linear combination of matrices of the type. See, the type of matrices that we take are, we take 6 matrices, namely A, 1, 1, because we want to somehow get the right notation. A1, 3, zero. Then we have A21. A22, 0, 0, 0, 0, 1, 0, and A23, these are the matrices that we take, and you can easily see that these are linearly independent with the usual addition of and scalar multiplication of matrices. So the collection set of 2 by 3 matrices of 2 by 3 matrices and spans hence a basis. Therefore, dimension of equal to 6, which can be conceived as That's an exploration that we have done. Now let us also try to invent some nice notations for this. We shall write Aij. Now Aij can be written as the matrix delta Ik delta Jn. You can check that for one. So you can check that each one of them takes this particular form, and this is a pointer to how we define the basis elements for the vector space LVW. Further, we also make some more explorations. We take E1, E2, E3 as the basis. It's a slight abuse of the notation that we are making. Basis for given by an ordered basis. As an ordered basis for R2. So also we designate by E1 tilde, E2 tilde, two cross one, where E1 the standard basis that we normally use. Then one can verify the following. I think I have written it elaborately in the last lecture, so I will just condense everything. You can verify this. Aij Ek equal to delta Jk this is what you get. For instance, when you take I equal to j equal to 1, so here what you have is this, that 1 I k 2 j 1 less than or equal to j l 2 j. So when j equal to k or k equal to j, you will get Aij Ej equal to Ei tilde. That is the notation. It's a very handy notation. And from this, I think you can get everything. In fact, what you have is that, for example, you have A11, E1 equal to E1 tilde, A12 E1 equal to 0, A A13 A11 0. So this is in the short form, etc. So what you have is that you're defining each one of this operator A11 or Aij as you run k over 1 to 2. 1 to I think I should use here k ranging over k ranging over 3. So k runs over 3 here. 1, 2, 3. Okay, so that you get this relation. A11 is defined by this because all that you have to say is what A11 does on a basis for the domain space. That we have fixed here. Once you fix that, the linear transformation A11 is defined on all vectors in R3 cross 1. Okay, or what we have designated by V, and so on. Okay, so I put a 3 dots here. I am not going to repeat it. Okay, so what you have is this. We can generalize the whole thing. Maybe some experience of generalizing this will give you some insight. Okay, so let us take A from F n cross 1 to F 1. Let A be given by Aij for 1 let E1 tilde be the standard basis for F. I'm working on the details to some extent because to give you an experience of how to do it. One should try to do it on your own, and if you can successfully do it without any confusion with the notations, then it's very good. Okay, now we translate this experience. So this experience can be translated as this is where we start. Okay. We define Aij as delta Ik delta J. So here 1 1 less than or equal to I k less than or equal to n, 1 less than or equal to I j okay. So this is what you have. Then we have, as before, one can show that Aij forms a basis for L which is equal to essentially the set of all matrices, all m by n matrices, therefore, or hence dimension of but all this needs some proof, because proving this is a basis exactly as you do here, you can do it. Okay. Okay, let us define. So here the operators that we define are Tij, El equals to delta I So for 1 less than or equal to I less than or equal to M, 1 less than or equal to J L. So this is the sort of operators that we define. So there are Mn linear transformations defined. It is Mn linear transformations. Bij's belong to L. This is what it is. And this collection forms a basis for the vector space L Fn cross 1 to Fm cross 1. That is from an n-dimensional space to an n-dimensional space. Okay, let us finish with that. So having done this, having fixed the notation, I think now we are comfortable to work on this. Okay, let us do that. So we write down the central theorem. Now we are comfortable to working with this. So we write down the theorem. Let V be an space and W be an m-dimensional vector space. Vector space order. Then LVW is a finite dimensional vector space of dimension this is the main theorem. Okay, let us see how we construct the proof of this. We can make use of this idea. So our exploration, the purpose of our exploration was to fix the notation. Let be an ordered basis V and be an ordered basis of W. This is m-dimensional, the other one is n-dimensional. Now for any pair of integers I comma j with 1 less than or equal to I, m, 1 less than or equal to j, and we define Tij from V to W by Tij of x k equal to 0 whenever k is not equal to k, this is equal to yi, or this is the same as what you have, delta kj y. Okay. So when j equal to k, you get yi. If j is not equal to k, then you get 0. That's the indication. Right? So this is the W. This is exactly the same thing that we arrived at here. Okay? So here xk's are to be replaced by this off. So that's the so these then for each I comma j, Tij defines a linear transformation from V to W, or Tij belongs to L W. Okay, so this is what we have, because what you do is, if we prescribe Tij at the basis elements of V, okay, then it defines uniquely a linear transformation. So Tij's are well defined. Right. Now our experience tells you that possibly Tij's form a basis for the vector space of all linear transformations from V to W. So let us write down that. Okay. Expect of working on elements of the basis for W. This is our expectation. Let us explore this. Now you see, there is one reason why we expect this, because after all, after some time we are going to say the connection or explore the connection between this m by n matrices and linear transformations from V to W, where V is say an n-dimensional space and W is an m-dimensional space. We are going to show that there are matrix representations of this type available for this class of operators. And therefore, our experience on working with these matrices is going to be exactly what we expect because of the connection between matrices, that is m by n matrices, and the linear space T or L VW. So that's what we are up to. Therefore, we explore the following. First statement. Let's start working the proof of this. Okay. Let us explore this. I am putting a question mark here, which I will remove after I prove this result. Okay. So let then for each L 1 less than or equal to L less than or equal to N, let A1L be the coordinates of TXL. So TXL, XL is an element of V, TXL is an element of W, therefore TXL is a linear combination of Y1, Y2, etc., Ym. Therefore, you have this relation TXL equal to sigma I equal to 1 to M A AIN Ym. That's the meaning of this statement. See that the matrices are just emerging from here. So let us mark this. Now this is true for okay. That is it. So this is the statement that comes from here. Now we show that T is then equal to Aij Ij. This is what we are going to prove. So let us investigate this. So let U be defined sigma I equal to 1 to M, J equal to 1 to N, Aij, Pi. We show that this is exactly the linear transformation T. So let us compute this. Then for each L, L less than or equal to N, u of xl is equal to sigma I summation over j aij dij xl acting over xl. Now this is equal to summation over I summation over j aij dij xl will give you essentially yi. Okay. So delta this one, which is equal to summation over I ain yi, which you know is essentially your d of which implies therefore that implies and now for this to be a basis, so it spans the LVW that we have seen. Now we have to show that this collection is linearly independent. So now I can erase this because I have proved this. Now what is the second part? The second part I have to prove is this. Tij is linearly so if U represented as a linear combination of Tij, something like I running from 1 to m, j running from 1 to n, aij, Tij equal to 0, then U of xl equal to 0 for every L such that 1 less than or equal to L less than or equal to L. Now compute this. So you make this operate over xl. So that will give you, so U of xl, this is equal to sigma I equal to 1 to m a I L y, which implies, and this equal to 0 implies, you know, this y1, y2, etc. ym form a linearly independent set. Therefore, you get AIL equal to 0, linear independence of y. So what you have is that all these AIJs are 0, which in turn tells you that AIJs are linearly. So together 1 and 2 implies is a basis for L, which implies dimension of so that completes it. Okay. We also work on the composition of, now we work with the composition of linear transformation, just like the composition of functions. Okay. So we take U, V, W as vector spaces over F of dimension M, N and K. That means dimension of U, dimension of V equal to N, dimension of so 3 finite dimensional vector spaces we take. Now we have then these spaces L, U, V is there, L, V, W is there, then possibly L, U, W is there. It is there, but we have to see what exactly how these are related. So what you have is this. This is U, this is V, this is W over the same field. Now you see that take a T from U to V, take an S from V to W. For U belonging to U, PU belongs to V. Okay, so before that, we define let's so these are functions from the two spaces V to U to V and V to W. So now let us work on this. Okay, so you can talk about S composition T. Defined as a function from U to W by S composition T of U equal to S of TU, which belongs to W. So you start with an element in U and then you end up with an element in W. So as functions, they compose and give you the function S composition T. The question that you ask is this: is ST, that's a question that you ask. Is ST linear? Okay, let's work out. So what do you want to prove? You want to prove that S composition T of U1 plus U2 equal to S composition T of okay, how to prove this? By definition, this is equal to S of T of Q. And this, you know, by linearity of T, this is S of TU1 plus TQ2. And that, you know, is just a function. S is also linear, therefore S of TU1 plus S of Q2. This is well defined. And what is that? That's equal to S composition T of U1 plus S composition T of U2. Now, where of course we have taken U1, U2 belonging to U1, U2 belonging to similarly, we want to work out this S composition T of alpha U is equal to S of T of alpha U, which is equal to alpha S of alpha of TU, which is equal to, because again you are using linearity here, alpha of S of TU, therefore this is equal to alpha of S composition T of U. And this is true for every U belonging to hence S composition T is belongs to L, U, W. It's a linear transformation from U to W. Okay. Right? However, remark, in general, Ts is not. That is because you see that Ts goes from the S goes from V to W, and there is no transformation T defined from W to Q, so it is not scale. Okay, right? That's a remark that you have. However, if U equal to V equal to W, say V, then T composition S and S composition T are different. And both T composition S and S composition T belongs to L, V, and we shall avoid repeating this V again and simply say we shall designate by LV You know that if V is n dimensional, then LVV is an n square dimensional vector space. Okay. Therefore, you see that both T composition S and S composition T are defined, or in a way, multiplication is defined in this particular space. However, in general, T composition S is not equal to S composition T, although both of them are defined. Okay. Right. We shall give an example for this to illustrate this point. We will make the following. These need not be finite dimensional spaces. Even in infinite dimensional spaces, you can define this. For example, let us take, you know that matrices are not commutative, so that comes here. So let us take let V be equal to set of all polynomials over the field F. Let D be the differentiation operator given by D of E in minus 1, where now we define TF. Then T is also defined from EF, PF. It is linear. Now you can show that BT is not equal to TD, and more precisely BT minus hence it is not necessarily that these operators do commute, as it is clear from the matrices. You know that if A and B are two matrices, n by n matrices, then both AB and BA are defined, but AB need not be equal to BA. You can give several examples for this. Okay, so I think I will conclude here. Thank you very much.